everyone. Welcome to the Algebraic Calculus 2 course. I'm Norman Wildberger. Today we're going to generalize the Chu Vandermonde identity to what we call the Binomial Chu Vandermonde identity. Here is the standard Chu Vandermonde identity in terms of falling powers. Alpha plus beta to the n falling equals summation k equals 0 to n choose k alpha to the n minus k falling, beta to the k falling. And I remind you that n falling means that we're taking alpha plus beta and we're multiplying it by alpha plus beta minus 1, alpha plus beta minus 2, altogether carry on like that until we get to alpha plus beta minus n plus 1. So altogether n factors, but they're all going down by 1 each time. And this identity here we saw was really at the heart of the Newton Polyseries identity. In other words, the generalized binomial theorem of Isaac Newton. This provides us with a kind of general proof of it. But also we've seen that this thing here has sort of analogs, that if we replace the falling powers with just ordinary powers, then we get the binomial theorem. So this is some kind of modification of the binomial theorem, because of course this is very familiar. And then if we modify it in the other way by considering rising powers instead of falling powers, so n rising, if we say alpha to the n falling is this one here, and alpha to the n rising will be alpha times alpha plus 1 all the way alpha plus n minus 1, altogether still n terms, but now increasing by 1 each time. So this also turns out to be a valid identity. We could call it the rising Chu Vandermonde identity. So we have these three identities which all have a very similar form, which is very intriguing. And it's especially interesting because we know this particular one is so crucial for the generalized binomial theorem of Newton. So it makes us wonder, well, is there some kind of analog of the Newton generalized binomial theorem or the Newton Polyseries identity that's sort of connected with these two formulas? And another thought that we might have is there some kind of way of interpolating between these three things? So today I'm going to show you that, in fact, what we can do is we can assign this initial formula to a variable, say t, with value minus 1 for that one, where this case here is the case t equals 0, and this one is the case t equals 1. In other words, we're going to be able to interpolate between these three identities. We're going to have a whole family of identities that interpolates and in fact extrapolates beyond these ones. But when t equals 0, we're going to get this one. When t equals minus 1, we're going to get this one. When t equals 1, we're going to get this one. And then that naturally makes us think, well, how can we generalize the corresponding generalized binomial theorem of Newton, which is really occurring at this level, to these other levels. So lots of interesting stuff happening today, especially as it turns out that we're going to, a bit of a spoiler, we're going to meet the exponential polyseries in this context as being associated to this binomial theorem case. So this is not just frivolous generalization for generalization's sake. We're actually uncovering a hugely important series which lies at the heart of a lot of mathematics for the t equals 0 case. And we're going to see that the corresponding thing for the t equals 1 case is in some sense some kind of sort of mirror symmetry version of the t equals minus 1 case. So lots of interesting things going to be happening today. The Chu Vandermonde identity is, of course, so important, so many people have thought about generalizations or variants of it. So even very recently, say H.W. Gould in 2018 wrote a paper involving a generalization of the formula, and M.J. Cronenberg just in 2021, also a paper. And in fact, Professor Gould has a lot of papers over quite some years in this general direction. So our take is we're going to be focusing on this particular approach to trying to generalize Chu Vandermonde, okay? We're going to call these, say, ladder powers. So I'm going to introduce a little bit of new terminology that looks a little bit funny, all right? So bear with me. So for n a natural number, we're going to introduce alpha to the n colon t. Alpha is, as usual, our standard Pauli number, okay? And this is some kind of variant on the power alpha to the n. And what it is it's alpha times alpha plus t plus alpha plus 2t, all the way up to alpha plus n minus 1t. Altogether, there's going to be n factors here. And the factors are all going up, or not necessarily going up because it depends on the sign of t. They're all changing in an arithmetical fashion. And clearly, if t equals 1, then we're talking about a rising power. So alpha to the n colon 1 is just what we're calling alpha to the n rising. While if t is equal to 0, all of these things here are 0, then we're just talking about alpha to the n. And when t equals minus 1, then we have falling powers of alpha. That's just alpha to the n falling. So yes, this is a way of interpolating between the falling powers, the rising powers, and the pure powers. And it's this particular thing that we're going to be using. Now, just a special case, what happens when n is actually 0? So it's not so clear what do we mean by 0 factors here. So this definition doesn't work so well. So let's single out this separate thing, agree that alpha to the 0 colon t is equal to 1 always. All right, great. So now let's introduce perhaps a new identity, a slightly bigger and better identity, which we are going to call the Binomial Chu Vandermonde identity. So it says that for n a natural number and polynumbers alpha and beta, so those are our standard bipolynumbers, and t also, in fact, a polynumber, we have this identity, that alpha plus beta to the n colon t equals summation k equals 0 to n choose k, alpha to the n minus k colon t times beta to the k colon t. So when t equals 0, then these are just the pure powers, and this is just the binomial theorem. When t equals minus 1, then these are falling powers, and we get exactly the Chu Vandermonde identity. When t equals plus 1, then these are all rising powers, and we get the rising Chu Vandermonde identity. So this single identity captures those three, but of course is broader because t can have arbitrary values. In fact, t is, at this case, just a polynumber, so we can substitute anything we want for it pretty well. So let's try to understand this by going up in degree in terms of n. So when n is 0, well, we've agreed that this kind of thing is always 1. So this hand side is going to be 1, and this hand side, the right-hand side is going to be 1. So we get 1 equals 1. So fine, it's not that interesting. For n equals 1, okay, then alpha to the 1 colon t, what's that? Well, it's just alpha, because it's only in the second term that you introduce the alpha plus t. So there's only one term, you're always getting alpha. So in this case, the left-hand side is alpha plus beta. And over here we have two terms in the sum. When k is 0, we get 1 choose 0 times alpha to the, this will be 1, times alpha to the 1 colon t, beta to the 0 colon t. And then when k is 1, we get 1 choose 1 alpha to the 0 colon t, beta to the 1 colon t. And what is alpha to the 1 colon t? Well, that's just alpha, and this thing here is 1. So this thing here is alpha. And over here, this thing here is 1, and this one here is beta, so we get beta. So the whole identity becomes alpha plus beta equals alpha plus beta. Okay, so it's at least correct, though it's not that informative. So here again, for reference, is the Binomial Chu Vandermonde identity. And now let's consider the case when n is 2. So the left-hand side, well, so let me just remind you, here's the meaning of alpha to the 2 colon t. It means alpha times alpha plus t. Okay, so that's the definition of this thing. Okay, so when n is 2, the left-hand side is alpha plus beta times alpha plus beta plus t. And over here we get the sum from k equals 0 to 2, so there'll be three terms, k equals 0, k equals 1, k equals 2. When k is 0, we get n choose 2 choose 0, which is 1, times alpha. So there'll be a 2, alpha 2 to the t, which, so this thing here, we get alpha times alpha plus t, and this one is beta to the 0 colon t, which is 1, okay? So we just get alpha times alpha plus t for the k equals 0 term. When k is 1, we get n choose 1, or 2 choose 1, that's 2. And then this term here is, well, there'll be 1 colon t up here, which is just alpha, and this is also 1 colon t, so that's just beta. And then when k is 2, well, we get something just like we did over here. We get beta times beta plus t. So this is the identity in the case n equals 2. So to prove this, of course, you just expand it out and see that it's true. But we want to prove it along the same kind of lines as we proved the Chu Vandermonde identity in our last video. We want to see it in a way that reflects the inductive aspect of this story. So we're going to prove this the following way. We're going to start with the n equals 1 identity, which I remind you was alpha plus beta equals alpha plus beta. And we're going to multiply both sides by this new term alpha plus beta plus t. So on the left-hand side, we get alpha plus beta times alpha plus beta plus t. That's that. Over here on the right-hand side, we multiply alpha by this thing, but we rearrange this thing now so that it's of the form alpha plus t first, then plus beta, while the beta term gets multiplied by the same thing, but rearranged so now that it's alpha plus beta plus t. Then when we expand that, we get an alpha times alpha plus t. We get an alpha beta from here, an alpha beta from here, so altogether 2 alpha beta, and left over a beta times beta plus t. So it's a very similar argument to what we saw in the Chu Vandermonde story, except that there's a t floating around, but it's not substantially different. So that proves the n equals 2 case. Okay, so let's look at the n equals 3 case. Alpha plus beta to the 3 colon t, that's on the left-hand side. And over here, it's like a binomial expansion of alpha plus beta cubed. But instead of having pure powers, we have these sort of ladder powers. So alpha to the 3 colon t, beta to the 0 colon t, plus 3 alpha 2 colon t, beta 1 colon t, plus 3 alpha to the 1 colon t, beta 2 colon t, plus beta to 3 colon t. Okay, and when we sort of write out what all these things are, the left-hand side is alpha plus beta times alpha plus beta plus t times alpha plus beta plus 2t, altogether 3 terms. And over here, well, okay, how are we going to prove this? So let's just prove it all at once, okay? What we're going to do is we're going to take the n equals 2 identity. The n equals 2 identity did not have this term. It just had these two was equal to this. So we're going to take this times this equals this times this. Okay, so this is a known because we're just using the n equals 2 case. And now we're going to do the same kind of thing. We're going to multiply each of these separate terms by this common term, but we're going to rearrange this thing in slightly different ways each time. When we multiply alpha times alpha plus t times this, we're going to write it as alpha plus 2t plus beta. When we multiply this thing by the same thing, we're going to write it as alpha plus t plus beta plus t. And when we multiply this one, we're going to write it as alpha plus beta plus 2t. And now it's easier to see that when we expand, we are going to get what we want. So this first thing here gives us an alpha times alpha plus t times alpha plus 2t. That's that thing there. Plus 3 alpha times alpha plus t beta. So we're getting one of them from here, alpha plus t beta, and another 2 of them from here, alpha plus t beta. The 3 alpha beta times beta plus t, we're getting 2 of them from here, alpha beta times the beta plus t, and another one over here, the beta times beta plus t alpha. And finally, what's left over is the beta plus t, beta plus 2t. Okay, so that's exactly what's appearing over here on the right-hand side. So we proved that the left-hand side is equal to the right-hand side, and that's a proof relying on the n equals 2 case. And if you go through this carefully, just make sure I've done it correctly, you will see that it's pretty obvious, pretty clear how to extend this. So I'm going to leave this as an exercise for you, all right? So write out the general case. So it's really not that much more work than the Chu Vandermonde relation to begin with. Okay, so now let's go back to the Chu Vandermonde story and the connection to the Newton Polyseries identity. Here's the Newton Polyseries identity, which also we could say is the generalized binomial theorem. 1 plus alpha to the r times 1 plus alpha to the s equals 1 plus alpha to the r plus s. And this is an identity of Polyseries, and it should have quotes around it. Okay, and let me remind you that the definition of this Polyseries had a little bit of funny notation. There was this kind of arrow bracket on the right-hand side suggesting that we're going in that direction, which is sort of what we're doing. And the definition of 1 plus alpha to the r in this case is the sum from n equals 0 onwards, so n equals 0, 1, 2, 3, and ongoing, of these powers of alpha with coefficients which depend on r. The coefficients are h sub n of r. These are the Harriot basis polynomials, and explicitly as polynomials in R, they are or can be written in terms of these falling powers, or r to the n colon minus 1. Remember, this is just our ladder power notation for the falling power r to the n falling. And there's an n factorial in the denominator. Okay, so that's what this series is. That's basically just the binomial expansion generalized to a general r, not necessarily a natural number r. And let me remind you that the proof of this identity, okay, the way we've set it up, came down to the Chu Vandermonde identity. The Chu Vandermonde identity is basically just exactly what's needed so that we can compare the power of alpha to the n on this side with the power of alpha to the n on this side. Okay? So the power of n, or alpha to the n on this side, will be r plus s to the n colon minus 1. While the power on this side, well, we're taking a product of these essentially polynomials, so we have to multiply the various powers of alpha so that they always sum up to n. So here's a power, here's another power, summing up to n. But they're all falling powers. And so it's exactly this identity which makes this Polyseries identity work. And this, for us, I remind you, is the case when t equals minus 1. So a very natural question for us is now, what are the corresponding Polyseries and identities for the more general BCV, Binomial Chu Vandermonde identity? Okay. Motivated by this, motivated by the connection between the Chu Vandermonde identity and the Newton Polyseries identity, it's really this one here that we're really interested in. This is a stepping stone to this, a way of understanding this. So now we have generalizations of this because we can modify that t. We can first of all send it to t equals 0, we can send it to t equals 1, and then in principle we could actually look at other values of t as well. So it's very natural for us to ask, okay, so in those other values, what are the corresponding Polyseries identities that are going to play an analogous role to the Newton Polyseries identities? So this is a very fruitful question. Okay, so now we're going to move to the t equals 0 case, which is essentially the binomial theorem, and that's actually the most familiar situation. And we're going to see that exactly this line of questioning leads us to what we're going to call the exponential Polyseries. So this is the Polyseries equivalent of the exponential function, which in most calculus courses plays a really central role in analysis. In fact, the exponential function is usually associated with Euler, who really developed it greatly. But we're going to see here that from this point of view, it's almost already implicit in the binomial theorem kind of machinations that Newton was involved in. We're going to see it just emerge naturally in this fashion. And I remind you, which I'll have to be doing quite a lot, that we're not thinking about these things as functions. Okay? These are not objects which input real numbers and output real numbers. No, these are Polyseries. This is like formal power series, like it's a combinatorial kind of approach. The combinatorials say generating function, so it's very much like a generating function point of view. Convergence of these series is not of interest for us right now. Okay, that's not at the heart of the matter at all. These are algebraic extensions of the world of polynumbers. Just they're polynumbers that keep on going in a way that we haven't quite understood. We haven't actually defined exactly what these kinds of things are at this point here. We're still sort of gathering data. Okay, so here of course is the binomial theorem. r plus s to the n equals summation k equals 0 to n choose k, r to the n minus k, s to the k. And we can rewrite this, and it's useful to rewrite it by taking this binomial coefficient, writing it as n factorial over n minus k factorial times k factorial, both in the denominator. And then bringing the n factorial in the numerator down here, under here, and then separating these ones, n minus k factorial under this one, and the k factorial under this one. So this is just a rewrite of this formula. But once we've done that, then it makes it very easy to see what the analog should be in this case of the Newton Polyseries. Okay? So we want to find the series for which this is the key point that proves an identity exactly of this form. Here's the required identity. We're summing polyseries that look like this. There's powers of alpha increasing, k equals 0 going on, so alpha to the k there. There's an r to the k, so you can think of r as a rational number here. And there's a k factorial in the denominator. So exactly that same thing is being repeated over here. It's the same story with the r replaced with an s. And I've just changed the index here just so we're keeping things straight and not getting confused. And over here on the right-hand side, it's exactly the same story again, but now instead of having r or s, we have r plus s. And so I'm claiming that here there's an identity here, okay? And that the proof of this identity is exactly this relation. It's exactly this relation that's telling us that if we look at the power of alpha to the n on the right-hand side, okay, the coefficient is going to be r plus s to the n over n factorial. There it is right there. And if you look at the power of alpha to the n on this side, well, you have to match up all these various powers here, that, you know, an alpha to the k with an alpha to the l, so that k plus l equals n. Or to put it another way, k is going to run from 0 to n, and l is going to be n minus k. Or if you prefer, l could be k, and k could be n minus k. Okay, so that's what's being expressed by this sum. This sum here is a sum of the product of coefficients here and coefficients here. So there's an r to the n minus k over n minus k factorial. That's a coefficient of an alpha to the n minus k. And over here, this is the coefficient of the corresponding alpha to the k. Those alphas multiplied to get alpha to the n. Right. So this binomial theorem, looked at this way, is playing exactly the same role as the Chu Vandermonde identity did, but now not to prove Newton's polyseries identity, but rather to prove this newish kind of identity, involving this new kind of polyseries that has some powers in the numerator and that has some factorials in the denominator. And of course, this is a very central object in mathematics and in calculus. And for us, it's a polyseries that emerges in this way. All right, so drum roll. For a rational number r, we now introduce the polyseries called the exponential polyseries in this way. Okay, it's going to be the sum from n equals 0 onwards of r to the n over n factorial times alpha to the n. And explicitly, that's 1 plus r times alpha plus r squared times alpha squared over 2 factorial, which is the same as 2. And then the next term, r cubed times alpha cubed over 3 factorial, which is 6, and so on. And just keeps on going in that direction. That's the polyseries that we're going to call the exponential polyseries. And we're going to give it this name here. There's an x in it. There's some brackets around it, and prominently there's still a pointy right bracket. So I want to use this to alert us to the fact that we're talking about polyseries here. We're not talking about functions. Okay? We're not talking about e. The number e at this point has nothing to do with this at this stage here. Okay? This is an ongoing poly number, which we're calling a polyseries, and we're giving it a name. And it depends on this rational number r. I'm going to put the r as an exponent. Okay, that's just the way, that's how we're just going to label this thing. And the alpha is not appearing because all our Pauli series are all in alpha. That's our standard, basis element that sort of generates the algebra of Pauli numbers and Pauli series also. So everything's always in terms of alpha. So there's no need to say that. Just like when we're talking about a Pauli series, we say a Pauli series P. We don't say P of alpha because the alpha is understood. Okay, and now we get to the exponential Polyseries identity, which is just now a restatement in this language of that formula that I showed you before, that for r and s rational numbers, x to the r times x to the s equals x to the r plus s. It's exactly the same identity, but now in terms of this language. And it's this identity that is proven by looking at powers of alpha and realizing that the required identity between powers of alpha on this side and powers of alpha on this side is just the binomial theorem. So this is the t equals 0 situation. We're picking up, emerging from the sands of mystery, the exponential Pauli series and this crucial property of it. So now we've completed 2 out of our 3 aims. We've sort of covered the first 2 of these identities. There's still the third one corresponding to t equals plus 1, involving the rising powers. Okay, so we're going to call these the Newton reciprocal Pauli series. And again, we're going to see a new kind of Pauli series come up. But it's actually not as new or different as the exponential is. We'll see that, in fact, the situation between t equals 1 and between t equals minus 1 are sort of like mirror images of each other in some sense. Okay, so that's clarified by just a little bit of algebraic manipulation, which is actually quite important and opens up nice, interesting investigations in combinatorics also, because we're essentially talking about binomial coefficients with negative entries. Okay, so here's the identity. So first of all, alpha to the n colon 1. This is the rising power. That's alpha to the alpha plus 1, all the way up to alpha plus n minus 1. And now let's look at minus alpha to the n colon 1. So we just replace alpha with minus alpha. We get minus alpha plus 1, minus alpha plus 2, all the way up to minus alpha plus n minus 1. And now let's take a multiple of minus 1 out of each of these n factors. So we're going to take minus 1 to the n out. So this then just becomes alpha. This becomes alpha minus 1 because we're essentially multiplying each of these things by minus 1. So this is alpha minus 1. The next one would be alpha minus 2. And this last one would be alpha minus n plus 1. Okay, but now we see that that's just a falling power. This is alpha to the n falling, or as we're writing it these days, alpha to the n colon minus 1. And there's a crucial minus 1 to the n out front. So we can reformulate this identity, summarize it here, that minus alpha to the n colon 1 equals minus 1 to the n times alpha to the n colon minus 1. So this is a way of going from falling powers to rising powers, or vice versa, at the expense of introducing a negative sign in here. Okay, so now let's go to our third identity, the third Chu Vandermonde identity, which is in terms of rising powers. Summation k equals 0 to n choose k, r to the n minus k rising, or n minus k colon 1, times s to the k rising, or s to the k colon 1, equals r plus s to the n rising, or r plus s to the n colon 1. Okay, so that's the rising Chu Vandermonde identity. And just as before, we are going to just rewrite it a little bit by unpacking the factorials which are sitting here in this binomial coefficient. Okay, so once we've taken these factorials around, the n factorials come down here. There's an n minus k factorial, a k factorial. Then the rising Chu Vandermonde identity looks like this. Summation k equals 0 to n, r to the n minus k colon 1 over n minus k factorial times s to the k colon 1 over k factorial equals r plus s to the n colon 1 over n factorial. Okay, now remember what the challenge is to cook up some Pauli series for which this identity is exactly what we need in order to prove a kind of a multiplicative property, just like we had for the Newton Pauli series identity and for the exponential Pauli series identity. And it's sort of obvious what we need to do, because we need to take these kinds of expressions and just use them as the coefficients of the alphas. So the identity that we're proving is this identity here, which has a sum of alpha to the k's with r to the k colon 1 over k factorial, and over here s to the l colon 1 over l factorial, and over here r plus s to the n colon 1 over r plus s factorial. So this identity, if we want to prove it, well, we'd have to compare the coefficient of alpha to the n on this side and the coefficient of alpha to the n on this side. Over here we're getting alpha to the n in a number of ways. In fact, n plus 1 ways. We can multiply, any value of k from 0 to n, but the L has to be the corresponding n minus k. Or I guess maybe it's easier to think of L as being k and k as being n minus L, or n minus k. So that motivates us to introduce this new kind of object, which is a Pauli series, which has the rising powers of r divided by factorials as the coefficients of the alpha to the n. Let me remind you that the Newton generalized binomial series, okay, looks a lot like this, except that there are falling powers of r right here in this numerator. Otherwise, it's exactly the same. So explicitly writing out a few terms, there's 1 plus r times alpha plus r times r plus 1 over 2 factorial alpha squared. The next one will be r times r plus 1 times r plus 2 all over 3 factorial times alpha cubed, etc. So that's our new kind of Pauli series, and it satisfies an identity just like this, okay? And we should give it a name. Okay, and this is the name I'm going to give it, and this is not just pulled out of the hat. What I'm just doing is I'm just rewriting this using essentially that reciprocal identity that we just have looked at. So I'm going to replace the r with minus r and the alpha with minus alpha. Okay, so that leaves that unchanged. And then this over here, this becomes minus r, this becomes minus r minus 1. And the alpha squared here is the same as minus alpha squared, so we don't actually have to put minus alpha squared. Over here we do, but not here. And then the next one, instead of having r times r plus 1 times r plus 2, we have minus r minus 1 minus r minus 2, alpha cubed, with altogether a minus sign, right? There should be another minus sign, sorry. Sorry about that. So we have to multiply over here by minus alpha cubed. Okay, all over 3 factorial. And when we look at it this way, now it looks like a binomial series, Pauli series expression a la Newton, because now we have falling powers. Okay, multiplying the rising powers by minus 1 turns them into falling powers. But now the starting point is minus r, and the evaluation is not at alpha but rather at minus alpha. So it makes sense for us to call this 1 minus alpha to the minus r. That's exactly consistent with what we're getting with this little manipulation. Great, so we've accomplished a lot today, okay? We've had, first of all, an extension, a unification of these 3 different Chu Vandermonde identities. And we've seen that just as the first one gives us the Newton Pauli series identity, which is basically the generalized binomial theorem, so the second one introduces the exponential Pauli series. And the third one introduces these things which we might call Newton reciprocal Pauli series, because there's kind of a reciprocal, but there's actually a minus sign here. So you could also think of this as 1 over 1 minus alpha to the r if you wanted to, and sometimes we'll see that that's an advantageous way to look at it. So great, so we've had a good introduction to some of the beautiful mathematics, essentially around the binomial theorem, really following in Newton's footsteps, and we're seeing some nice identities, and we're starting to get a little bit more experience with these polyseries, even though we don't exactly officially know how to think about them absolutely, but that's a to-do. So there's much to learn. I'm Norman Wildberger. Thanks for listening.